Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So I have a fear that I'm going to share with you. Anytime I have to take some like a hot pot off the stove or
Mhm.
pull the rack out of the oven or something, I think about that, the dishcloth or the oven mitt or whatever. It's just made out of fibers, and fibers tend to catch on fire. And as long as I can remember, I have had an invasive thought in my mind that's well, if I hold on to this rack for too long, it's going to catch on fire. And that
Mhm.
seems like it's probably not true. One, because it hasn't happened, and two, because you wouldn't make an oven mitt out of something that catches on fire easily. And
That's fair.
so that got me thinking, what actually is the what do you call it? The flashpoint, the combustion point for common things you would have in the kitchen. So your oven mitts, your dish towels, could the oven even get hot enough that I go to pull out the Thanksgiving turkey and it just shoots up in flame? I don't think so, but I know a guy.
Well, darn it, Lions. I'm a chemist, not a physicist, I think, probably, But with my very limited knowledge and very limited expertise, I will attempt to answer the question I want to answer, which is how long you would have to leave that thing in contact with the surface in order for it to reasonably catch fire. Because I think that that's really where the fear is it's not the how hot would it have to be, it's the how long would you have to have quote unquote screwed up and left the thing in contact with the heating element.
Yeah, because there is definitely you're pulling out the rack, and I try to do it quickly so I can let go as fast as possible. So yeah, time maybe is the actual factor I'm concerned with.
Yeah, and do you? So this is a side note. Do you ever do the thing where you've heated something in the microwave and it's really hot, the container's hot, and instead of getting the proper thing to pull it out of the microwave, you do the thing where you try to touch it with only certain fingers and rotate through your fingers. That way no one finger gets too hot.
I don't know why you're just describing the correct way to take something out of the microwave. What is your question?
Yeah. It's just the same way as when something's really hot, when you pull it out of the microwave and it's scalding your flesh, you go, quick, put it in my mouth.
It'll be sits in there.
Yeah, exactly. It's wetter in my mouth, I guess. I don't know. I don't know. Anyway, I've never burned anything inside my mouth before. But yes, so let's talk about this, because when you originally posed the question, of what the temperature would need to be, I was like, well, yes, that is a absolute factor of it. But I was like, well, then we have follow-up questions, because in order to answer what the temperature is, right? That's pretty straightforward. But then that's not exclusively the problem, as we'll find out. And then in order to really kind of answer the question you were asking, I had to answer 3 other questions, and then I kind of answered this one along the way. So I was like, you know what? Let's throw it all together. So let's just throw out some disclaimers. One, do not stress test what we're about to discuss, right?
Good one. Yes.
Yep. Don't put things on hot stuff in the attempt to figure out how long it will take or whatever. If you do wish to perform this experiment, please do it, with all of the proper safety attire. Don't just, throw some stuff on your stove and see what burns. So keep in mind also too, with anything that we discuss here, is that we are talking about pure substances, right? Not contaminated substances. For example, if we're talking about a cotton rag, is different than a cotton rag saturated with oil, right? Those are two different things.
Yes.
And, chances are the things in your kitchen are not the pure substance because you've used them for things, So, now we got all that out of the way. So interestingly, so what do you think, let's talk about this for a second. So there's really 2 or 3 things that we need in order to kind of figure all of this out. So I'm going to pitch it to you and see if you can kind of, guess at what the thing is. I'm sure you probably won't get the actual name. If you do, then the extra bonus points. But you kind of describe what you think that we'd need, and then I'll kind of either say, yeah, you're on the right track, or no, you're way off.
So I guess you have the material and whatever its factors are, right? So it's cotton, it's made out of cotton, and it's got these properties. You've got the thing that's generating heat, So
Mhm.
let's say like the metal rack in the
Mhm.
oven, and you have the oh god, we just talked about this. Like it's the rate at which it can transfer heat.
Yes. Yes. Okay. So yeah. So the first two, yes, those that is true. But you kind of hit with the third one. That is one of the three big things that you need is the rate at which the heat can transfer to the material. Right, is really important. Interestingly, so we've talked about this before, where the heat is a measure of the kinetic energy in the system. Right, and that is true. But the thing is that the amount, if you say this thing is 200 degrees Celsius, right? That is a measure of the kinetic energy in the system. But it doesn't mean that it has the same amount of kinetic energy as something else that is 200 degrees, which is kind of interesting, right?
Yeah. I don't. Okay. I mean,
Yeah.
I understand the words you said.
That doesn't quite make sense. But if you think about it, right? Like, let's say that you were to take a liter of air that was heated to 200 degrees and a liter of water that was heated to 200 degrees. Which one of those two things is going to burn you more by pouring more energy into you if it were to be poured on you?
The water.
Right, because
Right.
it has it requires more heat in order for it to change its temperature, which is the amount of heat in order to cause a temperature change, or the specific heat capacity of the thing. And then you need the temperature of combustion, right? So basically, is you need to know how fast is it getting poured into the material. As the heat's being poured into the material, how fast is it raising the temperature of the material, and then what is our endpoint? So you kind of need to know all three of those things, and man, that's a lot of variables, right? So I pulled together a spreadsheet because I had to look all of this up. And literally I was sitting there like, and I'll tell you what, man. So one of the things you need to know is thermal conductivity, right? So in order to determine the rate of heat transfer, which, if you had to guess, what would be the units for the rate of heat transfer?
Well, rate. So it's got to be like something over time. So
Yep.
like, I don't know, like BTUs over seconds or like therms over seconds.
Yeah, you got it. Absolutely. Those aren't the SI units, but you got it, right? So it would be joules per second, right? Which is a watt.
Oh, yeah. Yes. I
Yeah.
sort of kind of knew that.
Yeah, so watts. So basically, watts is the rate at which energy is being transferred, in this case, heat. So you then need to know a couple of other disclaimers. One, where I got some of these constants from, I didn't triple check the source. So some of the constants I used may be a little bit fuzzier than I'd like them to be. Eventually, I did find a source as I went through some of this, and was like, oh, this is probably a good source. I did not go back and redo all the other ones, especially because for some of the ones I was using, I had to scrape a lot of the internet, because finding the thermal conductivity constant for cotton is, it's like, well, there's a lot of factors to consider. I'm like, ballpark it for me. I don't care, And then, they were like, well, in terms of the raw material, but then in the process material, I'm like, oh my God. So, eventually I found something where I'm like, sure, this sounds, given the other thermal conductivity constants I found, this seems directionally correct. So I was like, whatever. This is all just kind of a thought experiment anyways.
And we know that you and anyone overhearing us is not going to test this.
Exactly. Right. So, absolutely. So you need to know the thermal conductivity constant. So basically, the rate at which heat is transferred, which is Q, is equal to the thermal conductivity constant multiplied by the area that the heat is being transferred over. So the larger surface area, the faster the heat will transfer. So that's in the numerator, right? So in the areas and this is where it got wild, because I had to make sure that I used the right units, or the consistent units. And man, the number of times I went back and I was like, wait, was I in meters or centimeters there? Okay. And, was that in milligrams or in grams or in kilograms? I'm like, oh my God. So, also places where I might have made some mistakes, but I did the area in meters squared, and I assumed it was 0.0001 square meters, which is to say roughly 1 square centimeter. So what I'm saying is, in this idea, what I'm saying is that you've left the stove on and you've carelessly tossed this material onto the thing. So it's not going to like probably land completely flat, right? And the reason why I did 1 square centimeter is because I'm assuming that once that ignites, it could ignite the rest of the material, right? So that's the
right.
fire
So,
starter.
Yeah, so you have like an ignition point, and then fire loves to propagate itself.
Exactly, right? Fire, like people, loves to propagate itself. That's how you can say like we're like fire, baby. But then, but only in that sense. But anyway, so then you take the delta T, so the difference between the temperatures of the two things. You know, because obviously the greater the delta T, the faster the heat is going to transfer from one to the other because of entropy. And so what I assumed is that you've left the burner on high, which means that it's going to be roughly 260 degrees Celsius, and that the thing you've tossed on it is room temperature at 20 degrees Celsius.
Right? I knew that burners were very hot. That is hotter than I thought.
Well, and actually, that's how the applicable heat, if you were to pull the element out and then just like leave it on, it can get even hotter than that. That's just how much heat it's actually like to the touch, you know? I think some of them I was reading for like the old ones that, you know, like where the element was completely exposed and they had no safety stuff, it would get up into like the like close to 400 degrees Celsius. I'm like, it never needs to be that hot. Nothing in the kitchen needs to be that hot. That's approaching like a muffle furnace. Like we don't. What are you doing? Are you trying to ash your hamburger? Because that's what you're going to do. Do you want to ash a hamburger? Because that's how you ash a hamburger.
I need this pot of water to be boiling, and I have no time to wait.
It makes me think of all of those Christmas movies that you see where it's like, okay, oh man, the family's coming over in 10 minutes. I needed to cook this turkey for an hour. Well, an hour at 300 degrees is the same thing as 10 minutes at 1800 degrees. Anyways, so yeah, so I use those two numbers, and then you need to know the thickness of the thing that you're talking about, because the thicker it is, it's divided by the thickness. So the thicker the material is, the more difficult it is to transfer heat. So I assumed it was about 1 millimeter thick, you know, since that would make the number, the heat transfer faster. So this is like on the safe side, if that kind of makes sense. And you know, that's roughly, you know, like most claws and things that you'd be dealing with are going to be in that ballpark between a millimeter and a centimeter. So, so that's what you need on to determine the rate at which the heat enters the material, right? Then we need to determine the rate at which the material heats up. In which case, you then need to know the mass of the material. So in order to do that, I had to back calculate it from density, because I had the volume that I was using from the millimeter thickness and the cubic centimeter. So I used the density to get the mass. You then need to know the heat capacity, which is constant I looked up. That would then give you, and then the delta T, which was established, we were going from 20 degrees Celsius to 260 degrees Celsius. Or sorry, it was going, that was the delta T for the material, right?
Right.
The delta T here is from 20 degrees Celsius to its ignition temperature, whatever that is, right? Because that's where we're trying to go.
That's where we care.
Yeah, right. And because what I was thinking, and this did not pan out, but I was wondering if there was somewhat of a constant between like, okay, sure, there are some things that may heat up faster, but the faster that they heat up, the higher they would need to be to combust, which would give you about the same amount of time, you know? So I was like, that's what initially tweaked my interest, was I was like, ooh, I wonder if you were to like graph these things, if it would actually just be like a flat line, like it's constant, you know? It wasn't, but you know.
But that's why we test things.
Exactly. So I went ahead and ran this for, the common materials that I ran it for was cotton, wool, polyester, and wood. I then also touched on granite, marble, and glass, because you had mentioned the idea of placing it on something, right? You know, and that also being a concern. So this would be the idea is that you've heated a pan to 260 degrees Celsius and then place the pan on the material. Or you're a crazy person, you cut a slab of granite and you threw it on your countertop and turned the thing on to see what happened. So top of the hour, cotton. So cotton has a thermal conductivity constant of 0.04 watts per meter Kelvin, which is the units that we need to use for this constant, right? You can always tell you're dealing with a constant when you've got just the weirdest friggin' units, because it
has to be generally applicable.
Yes, yeah. So it's just like if it's like what are the units? It's like, oh well, joules per second. It's like, oh, I could see that having a practical application. What are the units? Watts per meter squared second cubed. Joules. And you're like, okay, that's a constant. What are we trying to calculate?
Foot pounds. It's like, wait, what?
Oh, that's unfortunately a real one.
Yes, it is.
Foot pounds. That's whatever. Anyway, so you know what? I could be so many flavors this holiday season. I choose not to be salty. So, thermal conductivity constant of 0.04 watts per meter Kelvin. Using all of the other constants that I had mentioned that we're keeping constant in this experiment, that would give you a rate of heat transfer of 0.96 watts. So 0.96 joules per second, which again, in isolation, doesn't give you a lot of information. The ignition temperature of cotton, and this was kind of interesting, is for cotton specifically, is it had a degradation temperature and an ignition temperature. So the temperature at which it caught on fire, but then there was also a temperature at which the fibers start to like catastrophically break down. And the interesting thing is that process is exothermic. So it can start, to your point, fire loves to propagate itself, right? So, so I was like, what, let's be conservative and let's pick the degradation temperature, because in theory, that is the temperature that it could hit and then it could start to self-propagate, right? And that temperature is only 96.11 degrees Celsius. So not super hot, And so that gives you a delta T of 76.11 degrees Celsius. And that would give you roughly 8 seconds-ish of holding on to the super hot thing, So before, in theory, it could start to degrade. And if you think about it, that kind of makes sense, because this isn't the ignition temperature, right? But if you think about like a cotton oven mitt, that you could pull something out of, right? Mine have some scorch marks on them, from holding on to stuff for too long, So roughly 8 seconds for cotton materials.
We are talking pure materials, right? So
right.
This is more like if you said, I'm going to pick up this hot pan with like my t-shirt. Whereas yes. I assume oven mitts are marginally more complicated than.
Well, and that's cotton. The thing is, I believe that the oven mitts are a lot of times made out of like wool or a blended material.
Right.
Yeah. So that, but to your point, right, is that this is why it probably wouldn't be a good idea to wad up your t-shirt and use it exclusively.
Right.
As the thing to get the hot stuff out of the oven, because it's not made for that. And after about 8 seconds, you're going to start to, to degrade your t-shirt. And if I remember correctly, the ignition temperature was roughly double that. So it would start to be in danger of reaching its ignition temperature after about 16 seconds, Now, considering it's probably about 1 to 5 seconds to pull something out of the oven or to manipulate something, it's not a really high risk in theory. But, if you were to haphazardly toss it onto the thing, it wouldn't take too long before all of a sudden your smoke alarm's going off and the thing's smoldering. But to alleviate your concerns, it's not something where like it touched it for a second and then burst into flame. So we can do dealer's choice next. What do you want to do next? Wool, polyester, or wood? We'll handle the ceramics until last.
You said wool, so let's do wool. All
right, wool. So wool's thermal conductivity constant is 0.05 watts per meter Kelvin. So so what that means is it's not that much more thermally conductive than cotton, right? It is slightly more thermally conductive, but that kind of makes sense based off of our wool episode, which people may want to check out, which is that like it does conduct away some heat from you because of the nature of the beast, right? So pretty neat. So that means that it transfers heat at 1.2 watts. So cool. So then the question is like, oh, okay. So then would you be better off using cotton instead of wool, or just pure cotton instead of wool blend? But the ignition temperature for cotton is 570 degrees Celsius. If we remember correctly, the one for wool is 570 degrees Celsius. The cotton was 96 degrees Celsius.
Right.
So roughly 6 times.
Yeah. So you'd have to really leave that thing on the burner.
Correct. Right. And really that is, so it is slightly more dense than its cotton counterpart, which means, and it has a slightly higher heat capacity at 1.14. So that means that you need, as opposed to the amount of heat needed in order to get near the combustion temperature of cotton, you needed 7.6 joules. For the same amount of wool, you need 81 joules. So your shirt tossed haphazardly onto the burner lasts about 8 seconds before it starts to degrade. The wool lasts 68 seconds, or over a minute. So,
well, and this is, I might have missed a number back there, but would the
no, wood's different. We haven't done that yet.
No, we haven't. Would the burner or pot handle or rack or whatever is the hot source, it's not at that ignition temperature, so it wouldn't ever ignite?
Yeah, it's a fair point. Yeah, it's not at 570 degrees Celsius, so it would need to be...
There'd have to be like build up.
Yeah, and actually, now that you mention it, that does point out a kind of a flaw in the way I approach this, which is that the delta T would be, in theory, I'd need to do a differential equation in order to measure
because it
how
would
the
change
heat
as it heated.
Yeah, exactly. But I didn't do any of that, so
we're just chatting.
We're just hanging out, But yeah, so to your point, right, is that like the wool is basically, for all intents and purposes, non-combustible,
Yeah,
so
which no one will test, and they will just take your word for.
Exactly, and that's why I would imagine that it's, again, like if you've got like oven mitts, right, you wouldn't want a pure cotton oven mitt. You want like something with like a wool blend, and so on and so forth. But yes, so that is wool, way less, way higher ignition temperature, and by extension safer around hot things than cotton. We got polyester and wood.
Oh, we got to do polyester because I assume a lot of things in the kitchen, if not today, certainly over the last 50, 60 years, were made out of polyester, right? Clothing, dish towels, oven mitts, right? Polyester is a plastic, and plastics are miracle materials of the future that will never have negative side effects.
I have never seen any negative side effect from any plastic ever. I don't think you could say that about anything. Anyway, so and basically I said, like, okay, so we've now covered the natural materials outside of wood, right? So we got cotton, wool, and wood with natural materials, and then with a synthetic material, polyester, and then we had the stuff we get out of the earth materials, right? Your granites, your marbles, glass. So for polyester, its thermal conductivity was basically exactly between cotton and wool. It was 0.045 roughly. So I was like, that worked out because I just kind of picked a random synthetic, and so that gives it a roughly midpoint heat transfer of roughly 1 watt. Its ignition temperature is 450 degrees Celsius. So similar to what you were discussing before, right? Where it's like you really wouldn't get there. But just for funsies, its heat capacity is higher than wool's at 1.34. And its density is roughly the same. So that means that when you chug all of that math, it gives you roughly 70 seconds if the temperature was going on to infinity. But again, its ignition temperature is above the heat of anything, in the kitchen. So I thought that was kind of funny because if you're, some bachelor, right, who didn't buy an oven mitt because, you're an animal, right? Yeah, right. I mean, you're 22 years old. You're in your apartment, right? You just graduated college. You're just above an animal, right? So if all of a sudden, you open up the oven, you're like, oh, quick, I need to get something out of here. And your friend comes in, he's like, quick, here's your shirt. You're like, wait, is that a polyester blend or is it cotton? I just like that, But anyway, so yeah. So synthetic polyester would be fine. Now, this is the thing, though, is that synthetic blends, right? Like, so you've got polyester, you've got acrylic, you've got nylon, you've got all of these different things. This is the interesting thing, is that, as we've discussed, is that polymers vary wildly in their physical properties. That's the whole point. That's why we're so obsessed with them, is that you can make something that is comfortable enough to wear and also something that is strong enough to be a headlight. Like those are the same thing. So I stress that, I ran polyester numbers for the sake of running a synthetic polymer. That's not all polymers. So, if you want, you can chug this math for other ones, or just, not use things for their unintended purpose. So I went ahead and did wood as well. So wood has a thermal conductivity of 0.13 watts per meter Kelvin, which gives you a heat transfer rate of 3.12. So if you'll notice, that's roughly 3 times more thermally conductive than the things we have been discussing thus far, right? So it conduct heat good.
I hate to do this, but what kind of wood?
Oak.
Okay.
Oh, sorry, no, mahogany.
Okay.
I specifically looked at mahogany. Yeah.
I was going to say,
mahogany.
I have not done like a ton of like campfires where I had to, but I do know that like you use different woods at different times in the fire to like, because you need more heat for like other things.
Yes. Yeah, no, I actually, I did make note. It was mahogany. I started with, I think I started with oak, and then I was like, oh, mahogany. I mean, like, let's get classy. Let's burn mahogany wood. To be fair, all of their specific
next time.
To be fair, all of their specific thermal conductivities and a lot of these constants were close enough,
sure.
To where it's like, it was within like 20% plus or minus. So I was like, these are.
This is a neurotic concern of mine. I'm not going to quibble over a few degrees.
But that means it is way better at transferring heat, right? And its ignition temperature is only 240 degrees Celsius, right? So that's reasonably something that could get hot enough to just suddenly combust, right? So with all of that in mind, and the density of mahogany is roughly 0.71 grams per centimeter cubed, giving us a total mass that we use of 0.071 grams. A heat capacity of 2.3, which is, again, also way higher than what we've been dealing with before. It's almost double. But so that's kind of what buys us a little bit of time. So for that one, time in seconds, 12 seconds, right? So, that's still an appreciable amount of time for you to have, like, left this thing on the burner. And, so you have some, like a bamboo, like a mahogany cutting board, and you've slid it over onto the thing by accident. You got a few seconds before, it starts to like smolder and then, actually catch fire. So, not too bad. And again, that's the pure substance. Probably if you're using a cutting board, it has some sort of a protective coating on it, which I assume would hopefully make it less flammable.
Asbestos.
How could it be bad for you? It has best right in the name. Oh, goodness. So then that brings us to our granite, marble, and glass. So I started down this road with granite, and I ran all the numbers for granite, and then I got to the last number I pulled, which is the ignition temperature. I just happened to pull that number last. And when I did, it said...
It's got to be either 4 digits or, like, not a number. Like, does granite melts? Does it burn?
So interestingly, granite does not have an ignition temperature.
Okay.
Right? Yes, there are ways to set granite on fire, but they are unlikely to happen in your kitchen.
Well, good.
If I remember correctly, trichloro I forget what it is. There are some chemicals that can oxidize things so heavily that they can oxidize like stone. Mm-hmm. And so by that, there are some chemicals that can oxidize things and make things burn that you would not traditionally consider things that burn, like concrete.
I'm sure there was some like very valid reason that knowledge came to be in like the corpus of human knowledge. But I would like to believe that grant proposal read something like, Gary said nothing would make stone burn. And I will spend any amount of money to prove Gary wrong. Please send $10 million to my university.
Interestingly, since we're just hanging out in this coffee shop, having a conversation, I actually do know the origins of chlorine trifluoride, which is one of the ones that can oxidize.
Are you about to out yourself as a supervillain? Because this feels like an incriminating way to start a supervillain origin story.
No, man. Look, who doesn't know how chlorine trifluoride is made and was made historically? No, it was actually originally created by the Nazis to turn bunkers into hot porridge. So
great.
Yep. And even the Nazis were like, I don't think we should be making this stuff, man. Like, oof. Yeah, that's not great, right? You know, because like they were like, I think that originally their goal was like something like 500 tons per month of this stuff. So the idea is that they carry it around and then like pour it on bunkers and completely melt the bunker and then they get in there. I think they made something like 50 tons in the entirety of the war. And just one other final interesting thing about chlorine trifluoride is that it's still used for like cleaning semiconductors. Anything you need cleaned within an inch of its life, it'll do that. But the way you store it is, I believe that you put it into like a steel a container, and I forget what the container has to be made out of. But what happens is I think it's steel. Is that when you pour the substance into it, it immediately scorches the inside of the container and then leaves a residue of metallic fluoride that's what, so like it then renders the inside inert. Yes. Yeah. It makes its own little container because the container that you're trying to put it in, it doesn't like, and then it fixes that. But yes, so to your point, right? It does not have an ignition temperature, nor does marble, nor does glass.
Glass will melt, right? Because
all three of them will melt.
you blow glass, so it's like no. Sorry, the thought I was having was
you blow glass
that melts. Sick burn, bro. I mean, sorry. What I mean is like the temperature at which glass melts is a temperature that like people work with because that's how we used to at least make stuff out of glass, right? And now it's mostly made like in a factory, but like that's. A human could be close enough to glass that is a liquid to work with it because that is how we used to work with glass. Whereas it doesn't sound like it was doing really good for the Nazis to be proximate to the stone melting goo.
Yes, exactly. But and to be fair, we know that granite, marble, and glass can all melt because that's how we get it. Like it comes from inside the earth, and then we do stuff with it. Which actually, goes back to the fact that I think we've evolved as a species to the point where, we should just be making our own stuff, especially if we're, making things up in comic books. We should maybe discuss that at some point. Or if we have, we should do an episode on made up elements and whether or not they're cool.
I'm going to get you a shirt that says callbacks.
But it's got to be with a Z. Callbacks. So those were some of the common ones. So just to kind of review, cotton, don't if you're going to use something in the kitchen, try to avoid pure cotton materials. That is the things that are the most likely to combust quickly, followed by wood. But I think that we all know that wood's kind of combustible, so don't leave wood. Yeah. And then outside of that, wood, polyester, things like that. Not again, don't leave them on hot burners for a couple of reasons. One is that these were the ignition temperatures, not necessarily the melt temperature, right? So polyester does and can melt, so you can make a huge mess. And on top of that, just because it doesn't ignite doesn't mean that you can't heat this thing up to being super hot and then throw it onto something else and cause other problems, right?
Yeah. Then just like touch it, right? Is like, oh, I left this on the stove. It is super hot. I didn't know that. And then I put my hand on it.
Yep. And of course, as we mentioned at the beginning, it could be like the synthetic polyester may not catch on fire, but all of the oil you soaked up into it will. And then it will seem as though the rag's on fire. And I'm not sure that you'll want to quibble the difference in the middle of that problem.
Oh my God, honey, this rag is on fire. No, technically the oil is.
That'd be amazing. It's just like, honey, the rag's on fire. Actually.
I would absolutely want that chiseled onto my gravestone at that point. What were his last words? It says here, technically the oil is. Oh man, what do you think he meant?
That's That's crazy. This is completely tangential, but one of my favorite comedians, Kyle Kinane, did a great bit at one point where he said, like, your tombstone doesn't have to be like accurate. Like, you can put whatever you want on there, right? He says, like, so for me, I wanted to just say Kyle Kinane, born, 1987, died in your arms tonight. Famous quote, must have been something you said. Because like that's not a great joke, but it's the best one you're gonna find in a graveyard, that's for sure. So if you think that's funny, you should go check out that bit.
This is good. I feel like even if your math is fuzzy, and surely most of the things I buy to use in my kitchen, someone somewhere thought about this so that I'm not buying oil-soaked cotton rags to take brownies out of the oven with. I think it still helps to know, like, okay, even in these extreme cases, it's like you're not, if you grab the dish towel because your oven mitt wasn't handy and you just pull the oven rack out really quick with that, it is not going to ignite in your hands. Probably don't test anything we said, but like that there is actually some relief to know, like, okay, it's probably fine. And there's a bunch of additional like consumer protection safety stuff that probably puts it like way, way, way past that kind of realm. This does remind me about a story I want to tell you about stupid people who keep like their mail and like newspapers and stuff in the oven. Yeah. So we'll talk about that. And then I will think of some other questions I would ask you about.